I started sharing my screen. Can you see
Yes, we
the?
can see the screen.
There's a lot of echo.
Bring on stage.
Not you.
Okay.
Yes.
Okay, he's here. He's
Okay,
sharing.
all right. So, Pierluigi, the floor is yours.
Okay, thank you.
Yeah.
Hello to everyone. Happy to join this workshop, even though if just remotely. I'm Pierluigi Del Nostro, and I'm here to present our paper, the CHAMEO ontology exploiting EMMO's multiperspective versatility for capturing materials characterization procedures, written by Gerard Goldbeck, Daniele Toti, and me. This work started within the Nanome Commons European project that has the goal of developing harmonized and widely accepted characterization methods with reduced measurement discrepancy and improving interoperability of data. To pursue this goal, protocols for multi-technique, multi-scale materials characterization are defined, and ontologies, tool for data sharing, and standardized data documentation are used. This project is coordinated by the Technical University of Athens, and the project organizations participants are here on the right. This work lies in the field of materials characterization, which encompasses a wide range of methods and related research communities, which has led to a proliferation of terminologies and data management approaches. And this heterogeneity of information and formats hinders collaboration between communities and the interoperability of data. Indeed, the huge variety and complexity of materials led to the formation of multiple communities around the materials characterization field. Then establishing different terminologies with typically focus on specific application domains. So it is hard to have an homogeneous information set in order to be able to easily answer to questions like who is the expert, what are the properties that have been investigated on a certain material, what was the sample preparation process for a specific experiment. In general, it is hard to find information about experiments. With this work, we want to contribute to the creation of a common knowledge framework for the characterization of materials, with the goal to develop a standard for documenting characterization methods, being both human and machine readable, to facilitate reusability and transferability of knowledge across different communities. The starting point for this work has been the so-called CADA, standing for Characterization Data, which is a document template developed to provide a standard structure for documenting material characterization techniques. The CADA has been developed in the Oyster project, following the template of a similar structured documentation for materials modeling called the MODA. And recently, CAD has been the subject of a CEN workshop agreement. There are four types of concepts that are used for the classification of different steps of an entire characterization workflow. That in the CADA are sections with subsections, as you can see here on the right. There is the user case, which includes the sample and the information on the environment of testing. There's the experiment, which represents the process by which the metrological chain is defined. And here the fundamental elements are the probe, the signal, the detector, and the noise. There are the raw data, which is the set of data that is given directly as output from the metrological chain, usually expressed as a function of time, position, or photon energy. And the data processing represents any process or sequence of processes by which the data are analyzed to arrive to the final shape, the characterization property. And sorry, my screen has stuck. Okay. Um, these are sections in the CADA document template, as I said, with subsection where to specify textual information. The CADA is then a step towards a harmonized and standardized representation of materials characterization methods and processes that is made of textual descriptions and then is easily interpretable by humans, but does not provide structured data for retrieving information on the characterization methodologies. Having such information represented by an ontology provides structured data, which are machine readable, improves information retrieval, which for the CADA is exclusively based on text search, and allows for semantic fair exchange of information. That's why we have moved from a document template to the characterization methodology ontology that we have called CHAMEO. For the scope of this ontology, it should be as much generic as possible. So we have started working on CHAMEO in the Nanome Commons project with people from different fields, taking into account different domains and characterization techniques. To define the scope and design of the ontology, we have considered different inputs, namely the definitions of the CADA terminology used in the CADA document template, the information about different experiments by collecting CADA documents filled by the different industrial partners, who were also asked to answer to competency questions to outline and constrain the scope of the ontology. And with the view to reuse existing knowledge, where there were standards that were useful for our purposes, we have used them. For example, the ISA 88 standard have been considered as a base to model the process hierarchy in the ontology. One relevant aspect that arose by analyzing how the various CADA documents coming from the industrial partners is that the way they were filled, let's say the type of information provided is subject to interpretation. And this makes getting the homogeneous information about the different characterization techniques quite hard. Um, the CHAMEO ontology is meant to address this issue by providing a framework for defining a clear machine readable documentation based on shared concepts and definitions. The CHAMEO ontology is not conceived to represent all the details about the various characterization methodologies. Rather, it models the methodological generic aspects that are in common across the different techniques. The more detailed modeling can be done by developing specific ontologies than by specializing the CHAMEO definitions. And that's why we call CHAMEO a framework. This approach is a modular design approach which increases the level of reusability and interoperability. Just to mention that the CHAMEO ontology development is also supported by a European Materials Modeling Council task group. This picture provides additional details to understand which is the role of the CHAMEO ontology in this modular design. It is a domain ontology, as we said, to capture methodological aspects of characterization methods. It is based on EMMO, which is a top and middle level ontology for applied science. I will briefly illustrate it later, and tomorrow there is a session about this topic held by Emanuele Gadini. Based on CHAMEO, specific method ontologies can be developed, for example, to model nanoindentation testing. Then application ontologies can model specific use cases, for example, talking about nanoindentation, the fatigue use case. So we said that CHAMEO is based on EMMO, which stands for Elementary Multiperspective Material Ontology, which has the goal to define a standard representational ontology framework for applied science. This work on EMMO was started by practitioners in material science and has been improved with a multidisciplinary effort in a number of projects under the governance of the European Material Modeling Council. The main characteristics of EMMO is that it is a fundamental top-level ontology, um, while at the same time assuming the existence of objects that cannot be divided further in space and time. That's why it is called elementary. It is multi-perspective, which means that it enables the scientists to describe the world by using different views or perspectives, and this gives EMMO a high expressive power and versatility. And the all the relationships in EMMO among the objects can be of three types: topological, connectedness; mereological, partudes; and semiotic, which means signs communicating a meaning. The most powerful feature of the EMMO is the commitment about the fact that there are no absolute definitions of the ontological nature um, of objects, except for the universe and the single um, quantum elements of which it is made up. The top level of the EMMO respects this fact and hosts a branch for perspectives to categorize things in many different ways. Here there is a sketch of the different perspectives in EMMO. Moving from right to left, there is the holistic perspective representing the relations between the whole together with the parts, which plays a role in composing the whole, and that makes it something more than a simple mereological sum. There is the semiotics perspective, enabling the representation of the process of defining a meaning for the data, documenting the methodology for data generation, the subjectivity or objectivity of the process, and the measurement or a modeling-based generation process. The physicalistic perspective represents things according to their physical form, for example, matter, field, solid, liquid. The perceptual perspective enables the representation of the data as they appear to the human perception. The persistent perspective classifies things following the classical object-process dichotomy, and combined with the holistic perspective provides concept like participant, component, stage, constitutive process, and so on. There is the reductionistic perspective, providing a means to describe the composition through granularity levels that can be used to syntactically describe the data. There is the data perspectives in EMMO, which defines entities according to the nature of the entity and the decoding criteria to be applied to the variation of the entity physical substrate. And it provides a means to distinguish between the different types of data, analog, discrete, classical, quantum data, uh, and between formal languages, software code versus applications. In this paper, we have described how the EMMO perspectives were important to represent the different aspects of the CHAMEO, of the characterization process. The characterization methodology is modeled as a system, an aggregate of interactive things, each of which with its own role during the characterization process. So persisting during that time, then here the persistence perspective was used to model the process in terms of process and objects. And the characterization process is made of sub-objects as part of a complex whole, the probe, the characterization machine. So here using the holistic perspective. The procedural aspect, which is important for operators of characterization, captured in terms of processes, stages, and operations, was modeled using the persistence perspective. And the potential existence of a strict sequence between the different steps of the project is modeled using the reductionistic perspective. Representing the sample and the specimen as materials, so using the physicalistic perspective, as well as participants in the characterization method, so using the holistic perspective. Tracking all the types of data, raw data, primary data, secondary data, so the process data, also the process data using models, are modeled using the data perspective. This data becomes properties of the material through a semiotic process where they are interpreted and a meaning is assigned, defining the property of the material. So the data become the characterization property of the material through a semiotic process. From here on, I show you some simplified high-grain diagrams of the ontology, where some examples of the use of perspectives is highlighted. Sorry. The process for getting to the final characterization process, characterization property can be a complex workflow modeled through the characterization workflow class, which is subclass of the EMMO process and can be a composition of different methods. So using the persistence perspective. Methods are process themselves and are sub-processes of the overall workflow, being also a special part, so playing a special role of it, so under the holistic perspective. Note that each CHAMEO characterization method can be divided into several EMMO stages following the nomenclature of the ISA 88 standard. Since, as I said, the CHAMEO ontology models the concepts that are in common across different characterization techniques, the most general stages are represented here. Here are some stages. For example, the specimen preparation stage, which is the process of preparing the sample for the characterization, for example, through machining, polishing, cutting, etc., which can also imply the use of a holder. The holder is modeled as an EMMO object, so using the persistence perspective, but also plays a role in the whole characterization process. So here using the holistic perspective. Here is the measurement process with the different types of data that can be produced, raw data, primary data, secondary data, as I said before. The raw data is a set of unprocessed data that is the direct output of the detector, usually expressed as a function of time, position, or photon energy. The primary data are data after pre-processing for corrections to, for example, normalize, harmonize the data. And the secondary data is a result of the application of a post-processing model, for example, the Oliver Farm model for the nano-indentation technique. All these data represented by these classes are subclass of the EMMO data. So here the data perspective is used. The secondary data became properties of the specimen through a semiotic process by means of which an observer assigns a meaning, a meaning to the data. To conclude, I have here presented CHAMEO, an ontology to model generic aspects of characterization methodologies, conceived to be a common framework for the development of ontologies related to specific techniques. And the paper has a focus on how the EMMO perspectives can be used to represent different aspects of the characterization techniques. Starting from CHAMEO, the development of ontologies and taxonomies related to specific techniques is ongoing. And CHAMEO, together with the specific ontologies, will be exploited in the Open Innovation Environment platform, which is under development within the Nanome Commons project, with the goal to collect data about characterization experiments in a standard way, and then to share knowledge across communities. Thank you for your attention. Open to questions.
Thank you. Thank you, Pierluigi. So is there any question from the audience? Yes.
Yes. Thank you for the presentation. It's very interesting to use EMMO and elementary multi-perspective aspect. In the definition of system you give, and it was the same in the previous presentation, what about the environment of the material? Because I think some properties of the material just appear or have to be considered in a given environment. For instance, corrosion depends on the internal structure of the material, but also of the relationships with some objects in the environment. And in your definition of system, there is no question about an environment. One additional remark is about the element, and I think by definition, okay, it's interesting to go to the element. An element is by definition not the system, by definition of a system, or by definition of an element also. But what about the question of the environment and the relationship between the internal structure of an object and the external relationship it can have with its environment? And how to model this?
I'm sorry, I don't know if I have got the full question because I can't hear you very clearly. If I understood correctly, you are asking about how we model the environment in a characterization process.
Yes.
Okay, so we have some dedicated classes to represent the environment characteristics, like pressure, humidity, or other environment characteristics, as well as the measurement parameters, so the input parameters to set up the characterization system for characterizing the material.
Okay, thank you.
More comments from Gerhard? Yeah. I am Gerhard Kopeck. I'm one of the co-authors. Just a comment also on element and system. So that's at the top level distinguished, basically. So yes, I agree. That's in EMMO, of course, the element is not a system. Yeah, but that's very, very much at the top. So probably didn't see that in the presentation here.
The system is
Yes, the system is a yes.
holistic. We can understand in two ways.
Yes.
Either we bring together different aspects.
Sorry, microphone.
Yes.
You mentioned also the holistic perspective, and I think we can understand it two ways. One is to bring together different aspects and try to explain the whole, but the system is not a whole, it's a part of a whole. Maybe it's so holistic.
Okay. We can discuss. I mean, of course, there is no universal, definition in that sense of a whole, because I mean, what is a whole depends on what is your system. So in that sense, yes, I don't think we disagree. So of the modeling of how we do it.
Maybe holistic is a dangerous word, I think. Sometimes it can be misunderstood.
Okay.
Perfect. So is there any question? All right, that's perfect. So thank you very much again, Pierluigi.
Thank you.
And now for people who are here, so it's lunchtime, and also for people online. So you can keep your stuff here. The room will be locked. So and for people online, so the afternoon session will start at 2:45 with a keynote speech. Okay, all right. So see you later. Thank you very much.
Thank you. Bye-bye.
Bye.